In this session, we talk about the first principle modeling using a pool heating system example. Here the objective will be to cover mainly the use of the conservation of energy equation. So, for this case we take the same example of the two pool system. We have pool 1 and pool 2. We have water coming in the first pool, overflow goes to the second pool. There is another water inlet for the second pool, and there is a water outlet from the second pool as well. Consider that we have a heating system here where we can directly manipulate the heat input to the system. Now, if we take this temperature in this pool to be T1, here the temperature T2, so this temperature will also be T1. Consider this temperature to be T2i, here also the temperature will be T2. Consider this temperature here to be T1i. Okay. Now, to find a model between, suppose we are concerned with finding a model between this T2 and the energy input through the heater. Okay. So, the objective of the model, so that is the step 1, to find model between T2 and Q. Now, so to do this in the second step, you see that we need to gather some process knowledge. So, for this case we need to figure out how these two variables are related. Now, if we look at the relation between these two variables, we see that Q will affect T1 and then this T1 will affect T2. Now, see that we will need two differential equation to describe the relation. Other assumption we will see that okay, we will have to make some assumption as well as we need some other information about the process regarding the area and flow rate and other things. So, those will be required. So, moving to the next step is the bulk part of this modeling exercise, which is developing model equation. Now, we know that we have three conservation principles, and we said that conservation of momentum will be most of the cases like this one will not be relevant. The second one will be the conservation of energy, and the first one is the conservation of mass. So, here we see that the temperature is there in the list of variables. So, we will need the conservation of energy definitely. What about the conservation of mass then? Now, for the conservation of mass, we see that we are only considering the one liquid here, the water. So, there is no relevance to the component balance. Okay. Also, we see there is no flow change here. We are trying to figure out the relation between temperature and the energy input through the heater. So, when we are trying to find out relation between two variables, we will consider others to be constant. So, if we even write down the conservation principles, so conservation of mass, there will be the overall mass balance relevant for this case. We see that for pool 1, we will end up getting F1i equals F1o, and for pool 2, we will get a steady state relation that so this will come from the overall mass balance equation. We see that there is no change in the flow, so there is no change in the level here, also there is no change in the level here. So, based on that condition, we get this relation. Now, directly let us go to the conservation of energy principle. So, in terms of rate of energy, we will simplify this equation to write accumulation equals, again this is rate of accumulation of energy equals in by convection out by convection, and then there will be plus heat energy generated by reaction plus anything heat addition plus work done. Now again I am writing this in a much simplified form. Okay. Now if you look at for this particular problem, what we have here, we have the flow in. So this term is there. We have the flow out. So this term is there. We don't have any reaction, so this term will not be there. We have heat addition, so this term will be there, and there is no work done of the system, so this term will also not be there. So we have a simplified conservation of energy equation for this case. Okay. Now if we look at the energy term here, how do we really express energy? We'll be expressing energy in terms of, we'll consider this to be internal energy. I'm not going into the thermodynamic details, and then which is expressed by enthalpy. Now enthalpy always we express in terms of delta H, which is given by m Cp delta T. You remember that here delta T represents the difference of temperature of a stream with reference to the a reference temperature. You can choose any reference temperature you want, but every time enthalpy is expressed in terms of delta H, meaning that the enthalpy difference with respect to a reference condition. Okay. So now if we express in this way, we can write down the energy balance for pool 1 to be, so the accumulation term will be, so the energy content in the liquid in pool 1, that's again m Cp delta T. So for m it's rho V1, that gives m Cp, and delta T is T1 minus Tr. So that's the enthalpy, delta enthalpy for the liquid content in pool 1. So its rate of change will denote the accumulation. Again the first term, energy in by convection, will be for this stream coming in. So it will be flow rate is F1I multiply by this rho, we will get the mass. Cp remains the same, and the delta T is T1I minus Tr. So that's the energy in by convection. So what's the energy out by convection? Same way we'll have so temperature of this stream is the same as the temperature here, so that's T1 minus Tr, and then we have the heat addition term simply expressed as suppose Q with proper unit. Okay. So that's for the first pool. So now look at the second pool then. So pool 2, so the accumulation term becomes rho V2 Cp T2 minus Tr again d dt. Okay. So there are 3 streams here, 1, 2, 3, 2 coming in, 1 going out. So but the first one will be rho F1 naught Cp T1 minus Tr. The second term will be rho F2I Cp T2i minus Tr, and the out term will be rho F2 naught Cp T2 minus Tr. So we have 3 coming in and 1 going out, and see there is no additional heat in pool 2. Okay? So there is no Q term there. Now we have these two equations. Now if we simplify these two equations, for this one we can get a little bit simplified way, so that we have, suppose this rho Cp, we take it out from each of this term by dividing it by rho Cp. So we'll have the simplified form as so if we take the derivative on the reference, it becomes 0. So dV1 T1 over dt will be rho Cp taken out. If we have from this, if we assume this one equals F1, so we'll have F1 here, and you see that this reference temperature, when both are the same, the Tr term will cancel out. We'll have we'll have F1 T1i minus T1 rho Cp. Okay. So that's because F1 naught and F1, F1i and F1 naught the same as F1. So this Tr terms will cancel out. We'll have T1i minus T1 plus Q over rho Cp. The same sort of simplification if we take for pool 2, you will have rho Cp gets cancelled out for each term. You will end up getting V2 T2 dt equals, we have this relation that F2 naught equals F1 in plus this will be F1 O, okay, which is equals F1. Okay. So we'll have this term, and this term. If we replace, say, suppose this term by F2 naught minus F1, so we'll have, suppose let's take a look at this, we'll have F1 naught plus, if I replace this by so now see here, we can replace this F1 naught by F1 using this relation. So we'll just simply write it as F1 here, and then minus the last term F2 naught T2 minus Tr. So if we look at this equation here, we have this term F1 Tr there having opposite sign, that will get cancelled. We'll have F2 Tr, and here is F2 Tr having opposite sign, that will get cancelled, meaning this all this T reference term will get cancelled, and we'll have this V2 term. For this case, we consider there is no flow change, so V2 will be also constant, so we can take that out. So we'll have for pool 2 a simplified equation V2 will be, we have F1 T1, F2 T2i, and F2 T2 and F1 T2i. So we'll have F1 this term F2I, F2O, T2 minus we have this term T2I. So, we have this simplified equation for this pool 2. What about for pool 1 then? For pool 1, directly from this relation here, we get V1 Tt1 dt simply becomes F1 rho Cp. So, see that this is a more general form, but that is not the exact standard form that we will be using. So, we will see in the next few lectures how to standardize this equation, but again together these two formulates the model equation relating Q to T2. Here again you see we have this relation between Q and T1 by this equation Q and T1, and the second equation is T1 to T2. So, the relation between T1 and T2 expressed by this equation. So, we will just simply put the, and for this case also T1 will be function of time, Q function of time, T1 will be function of time, T2 will be function of time. We can assume some other values to be constant, but again we will see in good details the notations regarding T, but that is the model equation between this temperature and temperature in tank 2 with the heat input in tank 1.